Chapter 18, we'll talk about refraction. In Chapter 17, you were introduced to the idea of the index of refraction. The speed of light changes when it enters a material medium, and when that happens, the light also bends. So when light goes from air into the fish tank, or from the fish tank into the air, the light bends, and because of that, you have a difference in the actual position of the pencil and the apparent position of the pencil. And that is due to refraction. In fact, if I put the pencil in here at the edge, we get an image through each side around the corner of the tank, and so I get a double image of the pencil. But now let's explore the properties of refraction using the ray box as we did before. So I have a ray of light come out of the ray box, hits this plastic block, and if we do that, you can see that the light is bent when it travels through the plastic block. And we can characterize the angle of refraction this way. If I draw the surface of the block, like so, and I'm just going to draw a couple of dots. Here's a dot for the ray that comes in, and it strikes the block right here. And I know the ray inside the block comes out right here. Okay? So now I'll take the block away, and this ray right here represents the ray of light inside the block. This ray right here represents the ray of light that was outside the block. And now I'll again draw perpendiculars to the surface. We always have to do that. That's our normal, because we always measure angles with respect to the normal. Okay? And I have this angle right here, which is my incident angle. And I have this angle right here, which is my refracted angle. And there's a relationship between these angles that's given in the textbook, and it's called Snell's law. But since the plastic is more dense than air, this angle, the refracted angle, is smaller than this angle, the incident angle. Now let's think about this. When the rays of light go through the plastic, they get bent closer to the normal when they go into the plastic. But when they go from the plastic into the air, they bend away from the normal. And if I change the angle of the block, I can change the angle of the light that comes out. Now, if I change it more and more and more, the refracted angle, the angle of the light that comes out of the block, gets closer and closer to 90 degrees. As that happens, you start to see some colors show up. I'm starting to get what's called dispersion. And that's something we'll talk about in the textbook as well. That's how you use prisms to make rainbows. But for right now, I want to consider this. What happens to the light if I were to turn this block to an angle bigger than this? And so now, this refracted light should be coming out at an angle greater than 90 degrees, but of course it can't. So when the light can't come out of the block anymore, it doesn't. In fact, it won't. Here's the question for you. What happens to it? The light comes in, it can no longer refract. What happens? We'll give you some choices. And in fact, you can get a hint of that already. Watch the light in the block. As I turn it and make it closer and closer to 90 degrees, the light that's coming out of the block is getting very close to a 90-degree angle, and you start to see light here behind it. This is light that's reflected from this surface. And in fact, if I turn the angle so it's sharp enough, the light is not refracted, it is simply reflected. The light comes in, hits this surface, bounces off, and ends over here. And I can prove its reflection because I can take this surface and I'll just replace it by a mirror. Here's the incoming rays, here are the outgoing rays. I'm going to take the block and replace it by a mirror. And what happens is this. The rays of light end up in the same place. And so I have reflection from the inside surface of that block. And that's reflection that we call total internal reflection. Because the light comes in and just bounces off here, it's totally reflected and it stays inside the block. Total internal reflection. And this is something else we'll take a look at in Chapter 18. But the total internal reflection is something which is incredibly practical, because these days signals for communication aren't transmitted electrically, they're transmitted optically through optical fibers. And if I have an optical fiber and I shine a laser in one end, it's totally internally reflected and carries down the fiber to the end. And so this is actually how the information of this video is reaching you right now. It's being transmitted by light down fibers via total internal reflection. So the material of this chapter is relentlessly practical. Now, when light hits a boundary between two media, it bends. And when I can bend light, I can use that to produce images. And that's something we'll do with lenses in the next segment.